Many apologies for the 15-minute delay. I intend to talk for about 4 to 5 minutes. I'm just going to try and give you an overview of elementary calculus and slightly less elementary calculus in lean. That means differentiation and integration. So I'm not going to try and connect every single dot, like in the early lectures in the week where you're learning things like if A implies B and A is true, then B is true. I more just want to give you a sense of like what exists in the library and roughly how things are done and some of the design decisions that have been made. Yeah, like many of the talks, I'm basing it on mathematics in lean and try and add some clarifying comments here and there. So, okay, so the first thing is we can talk about differentiable functions and we can differentiate functions, which is good. And when I when I think about that, I often informally I would say something like, maybe I have a function f, and I might say, the derivative of f at x is equal to y, and carry on with my life as an informal mathematician. But formally, I kind of regard that as like actually making at least 3 statements, which are obviously related but not quite the same. So, the first one maybe is that, well, f is actually differentiable at x. And then the second statement is that, the derivative, so if it's differentiable, it has a derivative. It seems sort of silly to highlight this, but the derivative at x is y. And then maybe the third statement is I can actually cook up an entire function f prime, and then, that parameterizes all the derivatives. And so f prime is, it's a bit unclear informally, right? Am I just saying that f is differentiable only at x, or maybe because I've written f prime, I mean that it's differentiable everywhere? So, as usual, informally, we're sort of only as precise as we need to be. But, maybe I mean, f is the derivative, is the name for the derivative function as a function. Okay, so that's like, roughly what I mean when I write this. These are at least 3 of the things that I might mean. And so, in lean, because in formal mathematics, even if you weren't on a computer, but especially if you're on a computer, you have to be very precise about these things. And so each of these items, number 1, number 2, and number 3, these have a corresponding definition and set of lemmas about them in lean. So the example that mathematics in lean is giving is to take the sine function. So, as always, I think by now it's like Wednesday, and I've been telling everybody I meet to like hover over things and click to things. But as always, when you're in part of the library that you're using for the first time, it's a good idea to hover over. Is sine what I think it is from the name? Well, certainly somebody has written a doc string claiming that it is. But maybe I don't believe that. So then I hold down control or command, and now I get a definition of sine. Okay, so I learn a little bit from this definition. But actually, what is the definition of sine here? Well, it's defined in terms of another sign, I guess. And then it's got this .re. So, what's happening there? So, I've been tactically talking for a moment to give Lean a chance to catch up. So once this orange bar reaches the position of my cursor, I'll be able to ask it, like, what's this RE thing? It's like, okay, so that's the real part of a complex number. Oh, so I guess what's happening here is we have defined real sign in terms of complex sign. So maybe I go one level deeper and have a look at what that complex sign is. Okay, so it's the same signature, except now, the input and the output are now both complex numbers, and this is what we'd expect. I mean, again, now we have to trust that the exponential is what we think it is. So you can obviously keep going, and eventually you'll bump into axioms. But so I'm doing that slightly just as a little exercise in like following definitions and so on through the library, and slightly to give just a little bit of detail on this particular function and how we've done it. Okay, so that's fine. But what about sine and what about its derivative? Well, maybe the most important part of this line is this has deriv at definition, which my cursor is currently slightly blocking.
Sorry?
Yes?
I'm actually curious where this starts. What is the exponential then somehow primitive?
Oh, do you want to see the exponential?
Yeah,
okay. Yeah, totally. Okay, so we go back. The exponential is going to be like, sum of like xn over n factorial. Yeah, okay, so I've just jumped to the definition of the exponential, right? It in turn is defined about some limit of a Cauchy sequence. of exponential prime. Exponential prime, well, that kind of, the only thing that can be is the power series. So let's have a look. And indeed, it's this.
Which I found useful when I learned about it, is you might not know this, but in the tabs, there's the first one that you guys open, it's straight font, whereas the exponential lean tab is italics font. And that means that this italics one is just, you didn't edit, you just looked at it, and if he clicks, it will disappear and open a new tab. And so it's kind of a temporary tab. Whereas if you want to edit it, you click on the name. If you click on exponential.lin, it becomes straight. Now it's fixed, so now it's some tab that you made work. So that
yes. Yeah, no, that's a really.
So when you navigate as you were doing now, you want.
Yeah, I want to like temporarily look at this and then forget that file. Yeah, no, that's right. So like, yeah, this is a feature. It's so far from calculus now, but it's all worth knowing. But this is a feature of VS Code in any language that you're using, but it knows that you often want to peek into a file temporarily and then forget that you were there and go back. And so it has a concept of a tab being open temporarily, and it indicates this whether or not the descriptive text is like italic or not. Yes, no, it's good to all these features that we sort of privately learned and you forget that you learned them. It's good to call them out. Okay, so then this is sort of the base definition for the exponential and therefore ultimately the sine function. And I wonder how familiar that looks to, you know, somebody who's been doing lean for a long time. You're like, oh, cool, that's roughly what I would expect. You know, if you want commentary on that, this says that given a complex number, I'm going to give you a Cauchy sequence of complex numbers. And a Cauchy sequence is going to be a sequence of values. So for every input n, I'm going to give you a complex number, and then it's going to be a proof that it's Cauchy. So there's angle brackets there on line 373, and the first part of the angle brackets is all of the bit up to factorial comma, and that's like a sequence of numbers. And then the second bit is Cauchy sequence x, z, and that's some lemma that somebody has proved above that this is indeed a Cauchy sequence. And so therefore we can get a value of the exponential. And you know, the sequence itself looks about right. It's like takes a number and then it, you know, these are the partial sums of, you know, what we know defines the exponential function. Okay, so I'm happy to take a lot of direction from if people have questions as we go. So we can even now go and look into why, you know, how we've proved that exponential is a Cauchy sequence, or we can bubble all the way back up and talk about Haas derivat. Yeah, okay, so so I'm gonna close this guy and pop back out of the stack. Okay, so we have Haas derivat. So Haas derivat, so let's have a look at what that takes. So this says, so, you know, this like, again, I use this hover feature quite a lot. So the bit that I'm focusing my attention on there immediately is this f, right? So, you know, there's some base types and there's some type classes, but like the input into that is this function f. It's a function from k. What's k? Now I look back up. K is a non-trivially normed field. So what's an example of a non-trivially normed field? Well, you know, R and the complex numbers and also the p-adic numbers. And you can, you know, if you want proof of that, you know, you can say, I could do it with example, non-trivially normed field. Will Lean be happy with that? It's going to insist that I actually spell the tactic correctly, so fair enough. But you know, so this in particular means that it makes sense to talk about derivatives over R and over C, and if I could remember the notation for the p-adics, I could fill that in there too as well. Okay, so you know, Haas derivat exists. So we're talking about a function from the scalar. So this is like a curve valued in what? Well, valued in f. That's a normed space, and then it also takes f prime. So this is like not the entire function in this context. This is actually just, you know, the candidate derivative vector at a single point x, and this is a prop, right? So the very last thing in the top part of there is like colon prop, and this is just saying that this Haas derivat is like a true or false statement that you can make that f prime at x is the derivative of f at x. So like, yes, go ahead.
Why does it assume that it's the sign of the reals, or the differentiate of the reals?
As in the, so sorry, to be clear, I'm not using the reals here. This is just any k, and I gave the reals as an examples. But do you mean why does it? Okay, right. How does it know? I mean, how does it know that this is the real sign? Yeah. Okay. So this is just because higher up, on line 6, we said open real, And so now that says that, when it sees sign, there's no global sign. So it's like, I don't know what that is. So then it tries, is there a set dot sign? No. Is there a filter dot sign? No. Is there a topology dot sign? No. Eventually it gets to, is there a real dot sign? Yes. Okay, that must be the one you mean. I think if I said open complex, now if I hover here, this is complex. And indeed, so, we're now using a different lemma. Now we're using the fact that like the derivative of the complex sign at the complex number 1 is the complex number 0. But conveniently, somebody has named those two lemmas, real dot has deriv at sign and complex dot has deriv at sign. So I don't even notice that I'm invoking a separate lemma when I change the namespace like that. Okay, but then something else does break because, well, which explicitly invokes R. So I'm going to go back to real. Okay, so we're not so interested in sign. I mean, it's a great function, but it's just an example to show that we have this prop. It's quite a lot of work, to create this. But it allows you to say that any function in your scalar is taking values in a normed space, has a derivative at a given point. So that's like, I guess that's like the equivalent to point number 2 here. So we can do that much. Then the next thing is we can make the statement, maybe we don't care what the derivative is. We just might want to know that it's differentiable. So that's like point number 1. And again, like, this has to be defined somewhere. So this exists. And then, right. And then we get to something which I think is a little bit more interesting, which is, the example here on line 16. And this is saying like deriv fx equals a. So, this is kind of a little bit more like item 3 here, where I'm allowed to just talk about like deriv f, without having to also supply a derivative and saying the derivative of this function is this value. I'm just allowed to talk about deriv f. So what's deriv? Again, it tells us. So it says that deriv f at the point x, if it exists, otherwise 0. So deriv, if you look at the signature of it, so in the top half of that hypertext, it takes in a function from the scalars into a vector space. It takes in a point in the scalars, and it gives you back a function, right? But there's no assumption that the function is differentiable. So how could this be giving you back a function, when you apply it to something that's not differentiable? So the design decision that's been made in the library is that we'll just give you back the 0 function. These are functions valued in a normed vector space. Therefore, there's a 0. Therefore, there's the constant function 0. And therefore, there's like a candidate junk value for the derivative if you ask to differentiate a non-differentiable function. So that's like the design decision that's been made. The alternative way of doing that would be to only allow derivative to consume differentiable functions. And so then you would have another argument to the deriv, which is like the function, maybe the value, the point at which you're looking for its derivative, and then a proof that it is differentiable at that point. That would be like design B that we have not opted for. And the reason is, the reason we like this junk value design pattern that we've used for deriv and in many other places is that ultimately, you're gonna have to prove that your function is differentiable when you have a mathematically meaningful statement to make. But you can defer providing that evidence to the last point at which it's needed by just using the junk value pattern in deriv. So whereas if you force deriv only to operate on differentiable functions, you're forced to give this to discharge this proof obligation as early as possible. So it's just a little bit more flexible to say, I'm not going to force you to prove the function is differentiable. Certain statements about deriv won't be true unless the function is differentiable, as we'll see later. And then you will have to provide that evidence, but you can do it later if you want. So anyway, this is like the same reason, it's the same as like we have division in fields. We allow you to divide by 0, and we define x over 0 to be 0. And we could have defined division to require you to provide a proof that the thing you're dividing by is non-zero, but then this would be awkward. And so like the example there, again, I'm just sort of giving it, this is not so much calculus, but I'm just kind of emphasizing, design decisions that come up. So if x and y are elements of some field, then we define what it means. We define x over y. But we know that something like y times x over y is equal to x. But this is only true if y is non-zero. So what will happen is there'll be there's a lemma somewhere in Mathlib that tells you this, but it will require the hypothesis that y is non-zero. However, just to make sense of this expression, we don't force you. And so we have the flexibility only to prove y is non-zero later on when maybe we want to invoke this property. And it's just like this with the derivative. There'll be properties of derivative akin to this, which, like, maybe the sum of two differentiable functions or two functions is the sum of their derivatives. That will require a differentiability assumption. But just to talk about it, you don't. So, okay. All right, so that's 1, 2, and 3, which I've just spent 15 minutes talking about. So we can talk about the derivative of a function when we have this derivative function, and here we have some examples exploring the API. These are telling you properties that we read in the doc string for the derivative. So if the function is, so the example on line 19 there is saying, if the function is not differentiable, well, then the derivative is indeed 0. If it has the property that it's differentiable at x and the value is a, then the derivative is indeed a. Okay, so that's fine. Here's something where we're beginning to say something, mildly useful about differentiation. If a is a local minimum of f, well, then the derivative vanishes. That's okay, something. So what is the, what is the strange thing about that? Can anyone tell me? That we haven't assumed that the function is differentiable. So that's kind of a bit odd, but you can see there's even some like accidental conveniences to allowing junk values, and this is one. And furthermore, Lean knows, it knows about maxima and minima and so on. Maybe I should, for now, get rid of that. We have, I guess, this is a statement of Rolle's theorem. So, if you're this is now for a real function, taking values in the reals. We all learned when we're 18 or whatever that if you're, or maybe younger, if you're smarter than me, but if you have a continuous function on a closed interval and it's the same value, well, then it has to turn somewhere. And again, we have this curious fact that we actually don't need to assume differentiability because the junk value is 0. You do need to assume continuity, obviously, because you could have like a linear function except at the endpoint that just jumps down, and then the derivative will be 1 the whole way, or -1 or whatever. Okay.
Sorry, could you maybe just go back to the previous example? I think I'm confused by the dot notation.
Yes.
The h dot derivative equals 0. H is a proof.
Yes.
Of a being a local minimum.
Yes. That's a really good thing to highlight. So dot notation. So what's happening here on line 27 is that there is a lemma, which I'll jump to in a moment, and its name is local min dot deriv equals 0. That's the fully qualified name of this lemma. And the statement of that lemma is that, if you have a local minimum at a, then your derivative is 0. You can refer to notations using what we call this dot notation because of the dot that appears there in line 27. And if you give it a term whose type is the name before the dot in the lemma, then it uses that to look up the name of the lemma. So here on line 27, h has type is local min. And so when I write h dot deriv equals 0, what Lean does is it first very quickly checks, is there a lemma called h dot deriv equals 0? And there isn't. Then it says, wait a minute, what's the type of h? It's is local min something. Okay, is there a lemma called is local min dot deriv equals 0? There is. It finds that lemma, and then in addition, it feeds in h as the assumption that that lemma demands. So if we jump to this lemma, so this is dot notation. It's usually very familiar to computer scientists because it's taken inspiration from probably C++ maybe was the first language to use this. And mathematicians usually find it a bit weird, but it.
So we have seen this before, just not for proof term.
Yeah, maybe not for a proof term. Yeah, and you can see this is the full lemma name. It takes this hypothesis, and so h dot this is a way of looking up the name and plugging in the hypothesis that it demands all at once. Okay, yes, so that's that. I'm going to slightly speed up because I feel like it's just good to give an overview of what's there as opposed to diving into every detail, but I still very much welcome interruptions and questions because I don't want to just be one of these people who plows on and loses the audience, unless I already have. Okay, so there's a limited amount of kind of almost computation that you can do, right? So we've written a few simple lemmas like, what's the derivative of x to the n? And so here we have a situation where we can say, oh, well, we have, the monomial x to the 5, and we're looking for its derivative at 6. Well, this is 5x to the 4 evaluated at 6, so this is this number, and indeed, we're able to discharge that. You should not. This is in a way a bad example because this is unusual. Typically, you'll have to do a little bit of work to work with derivatives, but the reason this works is because somebody authored a simple lemma, and the more the library grows, the more of these lemmas accumulate, and actually the more this sort of thing happens. There are similarly simple lemmas, so we can work out the derivative of sine as at pi. So in other words, it knows the derivative of sine as cos. I mean, in fact, we can even ask this. I think you know this stuff, so there's no point. But if I do simple question mark and I bring back this, it's using the these two lemmas, that the derivative of sine, okay, and then it's using the cos of pi. So that's doing what we expect. Differentiate cos and so on. When I was making these, I noticed, I was like, oh, I wonder, I didn't know yesterday that this many, that there were exactly what simple lemmas existed. So I added this cos example. I was like, oh, cool, that works, and cos of pi, cool, that works as well. Can I do the derivative of sine at 0? Yes. Can I do it at pi over 2? Yes. I can do it at pi because that's the example that we had in line 41. What about 3 pi over 2, the sort of the last candidate? And this fails, but you can just add the missing simple lemma. And okay, so now I need to prove this lemma, but this is not a lemma about differentiation. This is just a lemma about the value of cosine. And now look, this was a failure a moment ago. Now this works, so it's picking up my new simple lemma. So again, if I comment out this new lemma again, line 54 now fails. There's red underline here, and if I click here and if I bring back the info view, I get an unsolved goal complaint from Lean. And then if I reinstate this new missing lemma, which somebody can add to the library, if you want, if you get bored at some point during my talk, then make a 2-line or maybe it'll be a 3-line PR and add this, and I'll merge it, and I'll be very pleased because clearly we should have a simple lemma that tells you about the cosine of 3 pi over 2. Okay. Say again. Or maybe we should have n pi over 2 for all, so yeah. Okay, all right, so that's like elementary calculus, but I grew up as a differential geometer, and I was often in situations where I'm considering infinite dimensional moduli spaces, and I'm ultimately I'm looking at different, derivatives of map between those. So I want to do calculus not just in one variable and not just in many variables, but like in infinitely many variables. And it's like a normal thing to do, for probably nearly a century in mathematics. No, I mean, I guess even Newton was doing it because he had calculus of variations. So we need infinitely many variables calculus. So does Mathlib have that? Yes, of course it does. All set up, I think, almost exclusively by Sebastian Goetzel. I hope I'm not writing anybody out of history there, but he did this kind of monumental effort to set up calculus, and he did it super generally. Okay, so now this is like kind of the same story again. You're going to see the same ideas appearing, namely there's going to be like has derivat, there's going to be a version of deriv, there's going to be a concept of differentiable, but they're not going to be these like specialized cases where they assume that your domain is just the scalars. They're going to be assuming your domain is just some normed, well, what's it going to be? It's going to be some space in which calculus makes sense. So today in Mathlib, that's any norm space. Of course, it's going to need to be a Banach space for certain results to be true, but you can make the different definitions just in the presence of norms. So, I'll quickly scan through. Some of you have seen this stuff already. Mathlib knows about normed groups. In this case, this is a normed group in additive notation that's commutative. So, this line in line 15 here, this is just saying, let E be a normed add commutative group. It therefore makes sense to talk about the norm of X as we do here in line 17. Norm has properties that you expect. It's non-negative. It vanishes if and only if the vector is 0. It's sub-additive as it should be for the triangle inequality. Of course, Mathlib also knows what metric spaces are, all these basic concepts. And so here, what's happening is Lean is, by the type class system, it's saying, well, if you're a norm space, you're in particular a metric space, so that's fine. Now, if I write lemmas about metric spaces, I can apply them in this norm space setting. It knows basic facts about the norm, like the fact that if you have a continuous function and you take its norm, so you compose, so you have a function from, in this case, x to e, and you take the norm, which goes from e to r, I get a function from x to r. Well, it knows that that's continuous because the norm is continuous. Okay, but we're trying to do calculus, and it's not enough just to have a norm. You also need, the key thing in calculus is that you you take a curve approaching your points near, more and more and more closely. So you need scalars so you can scale along that curve. So we need normed spaces. So what's a normed space? Well, this is a normed vector space. So, but the key thing here is now we're bringing in the action of R. This is an example, so we're restricting to the reals, but of course we can talk about a normed space over any normed field, certainly, and possibly more generally. I'd have to, well, actually I can ask Lean. Yeah, normed field is what it requires. So that includes if the reals are complexes of the p-adics, the three cases that always come up. Again, this obeys the axioms that you're expecting. Scalar multiplication, here, dear. The hovering is good except when it's not. We know basic undergraduate facts, like if you're finite dimensional and you're over complete scalars, then you're complete. So the reals are a complete normed field. And so therefore, on line 37, if I assume that E is finite dimensional, then I get the fact that E is complete. So that's great. I'm not going to have to add a bunch of completeness hypotheses to my theorems about calculus in finite dimensions, because Lean will automatically just know that it's complete, and so the various limits that I'll want to take in the process of making derivatives will just work. Okay, and then blah, 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 further properties that you would expect. Okay, now we have generalized to any non-trivially normed field. So this is a normed field where, actually, it's exactly this statement on line 42 and 43. It's a normed field where you have an element of norm strictly bigger than 1. This is the critical thing that you need to do calculus, because you want to scale your points closer and closer to the target point at whose derivative you're looking. So you need a function whose norm is, well, I guess, bigger than 1 or less than 1, either way around. But so it's an extremely mild condition that just rules out pointlessly normed fields. Okay, blah, blah, blah. Again, I'm just skimming over this, just trying to give you a sense of what's there. But stop me if you're especially interested in some point that I'm skipping over. Okay, so now, I claimed that we're going to be talking about calculus in infinite dimensions. I've just talked about normed spaces. That's great, because they're going to play the role of both of the domain and the codomain for our functions that we're going to differentiate. But we also need to talk about, what's the type of the derivative? Well, the derivative, of course, maybe you think first in finite dimensions, it's a matrix of partial derivatives. You have dfi by dxj. In other words, it's a linear map from your source space, your domain to your codomain. In infinite dimensions, we know that there's a topology there, so you can't just have an algebraic object, so you better use it. So the derivative should be a continuous linear map. So this is why we're talking about continuous linear maps here. Okay, so fine. So Mathlib, for many purposes, needs to know about continuous linear maps, and indeed this is exactly the type of derivatives. So we have a bunch of theory about continuous linear maps. I'm just going to skip over this because mathematically it's not terribly interesting. Just reassuring you that indeed Lean knows what it should about continuous linear maps. It's kind of worth highlighting line 73. This is like F here. Yikes. F here, is a continuous linear map from E to F, little f to capital F. And so we're talking about the norm of F here. So, we do indeed have the operator norm. So this is like a basic thing, but, this example on line 73 is evidence that we have the operator norm, and indeed the combination of these next two examples proves the operator norm does indeed have the characteristic properties of the operator norm. Okay, so we've got the basic machinery that you need to be able to talk about derivatives, and then you need the definitions. Again, I think it's worth just outlining that they are the shape of them is what you would expect. So first we define asymptotic notation. We do this with respect to filters. So we can talk about, look here, for example, we can talk about what it means for F and G to be, big O, or F to be big O of G. This is the big O. L is a filter. So filters are this way of not having to separately deal with limits of maybe you're going off to plus infinity, or maybe you're taking a left-handed limit at a point, or who knows. So, or maybe you're talking about a sequence and you want to talk about the at-top filter and the natural numbers. So again, reasonably general setup, but it allows us to like do things once rather than many times. So we have big O notation, we have little o notation, which is what we're going to need for derivatives. And we also have the, these f and g are roughly the same size. In other words, f minus g is little o of g. Okay, so, blah, 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 very, very patient, careful people have put in place a bunch of definitions which then finally allow us to talk about being differentiable. So we previously, we started off with like has deriv at. Here, the difference is there's an f, right? This is has f deriv at. And the f is for Fréchet, who was this, I guess, French dude who was very, very keen on functional analysis. And so we talk about the Fréchet derivative in his honor. And so it means, in Mathlib, it just means the multivariable derivative. So here, little f is now a map not from k to f, which is what we had previously, or from r to f, or from c to f, but from e to f. So there's multiple variables in e. And we can talk about its derivative. It ends up being a continuous linear map. So this is the notation for a continuous linear map. And has f deriv at is just the notation for saying the derivative of f at x0 is f dash. And, is it what you expect it to be? Indeed it is, because this statement here, has f deriv at, is equivalent to the statement that f of x minus f of x0 minus the candidate value of the derivative times x minus x0 is little o of x minus x0. So this is, if you, on paper, I would probably divide the whole thing by x minus x0, and I'd get, f of x minus f of x0 over x minus x0 minus f dash is little o of 0. Okay. What else do you want to do with derivatives? Well, we like to take iterated derivatives. So, if I have a function f from e to f, then what's the nth iterated derivative? Well, I can take it at any point. So I might be talking about the derivative of any point x in there, and then what I'm supposed to get, I guess, is a multilinear map from e cross e into f, and this is a multilinear map. So n times. So right, so there's notation for that in Mathlib, which is like e, in brackets times n. So this is how we indicate. And maybe I should bring back the info view, so we can actually ask Lean a little bit about this. Okay, so actually in the goal view here, it's even correcting me. It's reminding me that I should be talking about a continuous multilinear map. But it's also explaining to me this notation. I'm actually mildly surprised that the notation doesn't appear in the info view. I thought I was going to have to click on the notation here and get it to explain it to me, but Eric could probably tell me why. Exactly. And I'll never repeat that gem of wisdom again. So it's okay, Eric. All right. So we have derivatives. We have some general. We have iterated derivatives. We also, of course, want the notion of continuous differentiability. We have it. It's called cont diff, for continuously differentiable. You feed in the scalars over which you're working, the number of times you're differentiable, and the function. It means what you think it should mean, blah, blah, blah. I want to say something about integration. So unless somebody wants me to continue on differentiation, I'm going to say the takeaway here is remember that there's really, a high resolution of concepts of differentiability. That's like, are you differentiable? What's your derivative? And there's this deriv function. And then we have like a special case because you're often working over the scales, like maybe you're looking at a vector field in a manifold, and this is a frequent thing that comes up. But then, of course, under the hood, everything's set up generally, and you can talk about, differentiation in as many dimensions as you like. And that's all I'm going to say about differentiation. Okay, and then I'm going to say a little bit about integration. Again. Yeah, okay, so I will say very little about that, but I'll say something. So over the reals, so there is, if you want the inverse function theorem to hold, and indeed we have the inverse function theorem, I think it's there, and you look at exactly what you need, being differentiable, over a general field, being differentiable and having a non-vanishing derivative is not quite enough. You need slightly more. So you need this concept of being what Mathlib calls being strictly differentiable. It's a fact. Nobody knows this, or like mainstream mathematicians know this, because strict differentiability and regular Fréchet differentiability coincide over the reals and the complexes. And so it's an invisible truth to those of us who never work over the p-adics. But over the p-adics, these are indeed different concepts. And if you want the inverse function theorem to hold there, you need the concept of strict differentiability. Because we want to support people to work in these domains, we therefore prove the inverse function theorem first for strict differentiability, and then we have specialized versions just for differentiability that invoke this equivalence over R and C in those settings. So unless you're, unless you're a p-adic person, strict differentiability is not something to spend time on. Okay. Integration. I'm going to give us slightly even more rapid because I'm down to 10 minutes. Skim over integration. Again, I appreciate that I'm going quickly over quite a bit of stuff, elementary mathematics, but it's a lot of lean. All I'm really trying to do is give you a sense of what's there and where to start looking and highlight a couple of design decisions that we've been made. So, I am aware that I'm kind of skimming, but I think it's kind of better to get somewhere. But, I'll also take guidance. Okay, so likewise, we have a theory of integration. Similarly to with differentiation, we have a general theory where you can integrate, of course, over any measure space. And more things are true over better behaved measure spaces. And then we have specializations of that to common useful situations, like, for example, line integrals are important things. And so we have got even special notation, as you can see here in line 15, for line integrals. So this is A and B are real numbers. And what are we integrating? Let's see if I can bring back the info view. So, we're integrating this. So this is a function from R to R. And we're integrating it over the reals. And, actually, I realize it's not so helpful. Pardon me? Here? I'm not sure if I'm understanding the suggestion, but yeah, thank you, sorry, yeah. Talking more than I'm thinking. I'm integrating x. Yes, thank you. And x is a real number, so this is the identity function. And then the result, of course, is x squared, and then this is a definite integral between a and b, so it's b squared minus a squared over 2. So this is evidence that we have an integral. Again, is this an integral? You can try to convince yourself of this 3 ways. You can trust that Mathlib is not built to confuse people and that we don't tell lies. You can go and look at all the definitions and convince yourself that these are correct. Or, which the most typical way, is you just look at the API for this and you observe that indeed it has the properties of an integral. So the fact that this gives you the correct answer for the identity function is some evidence in favor. It gives you the correct answer for 1 over x. This should be log. Again, this is just advertising the sorts of things that can be done. So better evidence is if you have a continuous function. So the example on line 21, I have a continuous function. I take its indefinite integral and I differentiate that. Well, then I get back the function again. So this is like a weak version or a very elementary version of the fundamental theorem of calculus. Okay, so this probably is an integral. And here again is an example of the convenience of deriv not requiring you to upfront provide an example that the function you're trying to differentiate is differentiable. Because we know if f is continuous, then its integral is continuously differentiable. And so I don't have to mention this in the statement of this lemma. It comes up in the proof, of course, but it makes this cleaner. I guess this is the inverse function theorem the other way around. So you don't differentiate an integral, you integrate a derivative, and then you get back to where you started. Okay, so this probably is. And then actually there's a really nice, quite deep, powerful theory of convolution. This is the simplest possible example of it at play here. But this star here, this is a special notation that is available when you say open convolution, which is why that's there. And then we have the convolution of 2 functions, which is the integral of those values that add up to a constant. Okay, so that's like elementary integration. And then just like with differentiation, now we of course want to integrate in much more general settings, and maybe we want to do probability theory like Remy does. So therefore we need basic measure theory. So this is the analog of having norm spaces so that you can differentiate. For integration, we want our norm spaces. So we have measurable spaces. So what is a measurable space? Measurable space is a space equipped with the sigma algebra. Maybe I'll peek at the definition just to see how that's said in lean. okay, indeed, right. Measurable space is a structure with, by the looks of it, 4 fields. One of them is a predicate on subsets. That's the measurability predicate. This predicate is true for the empty set. Okay, that looks right. It also has the property that if S is measurable, then the complement is measurable, right? That, I believe that's a property of sigma algebras. And then, countable unions of measurable things are measurable, right? So here's the union happening here at the end of the line. So, okay, yeah, that looks like the definition of measurability. I see the way countability has been implemented here is just, it's a function from our sort of default countable object, namely the natural numbers. Yeah, that's one way to do it. Okay, so that's measurable space is what I think it is. Again, in it, you can either look at the definition or you can do what's happening here. You can observe the API. Right, so there's some basic stuff about countability here, which I'm not actually going to be so fussed about. Yeah, basic things we all learn on day 1 of sigma algebras, like it also works for intersections. But okay, that's, why do you want measurable spaces? Well, because you want a measure. We also have measures. And yeah, there's a little bit of content on line 38. So a measure, so if I look here and I bring back the info view, so the left-hand side here, mu of S. So what's this? Well, it's an ENN real. So that's extended non-negative real number. So this is a real number from 0 up to and including infinity. Okay, so that's right. That's the correct place where a measure should take values. It's a little bit surprising here that I haven't assumed S is measurable at first, at least if you're not used to the way we do things in Mathlib, because we're taking the measure of a non-measurable set. Again, it's this junk value pattern. Certain lemmas are only going to be true if you have a proof that S is measurable, but just to make the definition, you don't need to. And actually, there's a somewhat meaningful definition to make, which is just, you can say this is the inf, so it's the smallest extended real number that you obtain by taking the measure of all measurable sets containing S. We know that really you should only take the measure of measurable sets, but by making a definition like this, you find that some properties still hold. Like, for example, subadditivity. I can have subadditivity for families of subsets here on line 41 without even having to assume any measurability, and this is just a consequence of the convenient kind of junk value design. But then, for genuine additivity of disjoint families of subsets, of course, this is not true, and this is the sort of reason why measurableness is a concept. Okay, so the main takeaway here is we have measure theory, and we have a deep and rich measure theory that many fancy results have been proved about. And then, finally, what do we do with that? Well, we integrate things. I mean, we do lots of things with that, but one of the things we do that is we integrate things. And so now, we previously saw the elementary integral where you're just integrating along a line, but indeed, if we now give ourselves a measurable space and we give ourselves a measurable, or a measure on that measurable space, then we can, again, like with the differentiability, you can talk about the integral, you can talk about what it means to be integrable, and you can talk about what it means for the integral to equal a given value. So it's a similar-ish pattern. So we have integrability of functions, basic properties that should be true are true, like the integral of the sum is the sum of the integrals, provided both of the functions are integrable. We have the dominated convergence theorem. You might mostly be believing that because you see us proving it with a lemma whose name contains dominated convergence, but I wonder how much, well, the input here is capital F is what's this? It's a sequence of functions, and little f is like a sort of a target function, and then you have this almost everywhere boundedness, and you have this limiting property, and so the limit of the integral is the integral of the limit. This is Fabini's theorem, I guess, right? So here we have a function on a Cartesian product, and we have measures separately on each of the two products. Like, so we have mu is a measure on alpha, and nu is a measure on beta. So we have products of measures. So mu.prod nu is a measure on alpha cross beta. So we can talk about the integral of f on that, and indeed this is with the various assumptions like sigma finiteness that I see here. this is indeed the iterated integral of first with respect to nu and then with respect to mu. So we have Fabini. Okay, so we have the basic things. We have convolution in this more general setting. I feel like Flores could give a really interesting talk on convolution just on its own, because it is a very nice theory in Mathlib. And then we have change of variables in a super general setting. So here, the key bit to notice is that we have like an absolute value of a determinant. So, you know, we're integrating f, or rather we're integrating g here over the image of a set S. And this is equal to, on the right-hand side, this normalization that you pick up as a result of changing variables, the absolute value of the determinant, times g composed with f. So this is like obviously super important theorem that Sebastian Gosel added to Mathlib. It's a really good example of going extra mile on Mathlib. I've seen Sebastian give a really nice talk about this, where he describes how he worked very, very hard to make the assumptions for this theorem as weak as possible. Like you can see here, we're assuming S is measurable, but we're assuming pretty much nothing else. Like we don't even assume G is continuous. We don't assume S is open. There are many, many assumptions that if you look in a book, usually these are all required, but Sebastian has worked hard and discovered that the theorem indeed still holds with only very weak assumptions. And I guess that's like the final thing I'll say as I run out of time, but yeah, that's a theorem like this is likely to be used many, many times in the library. And so if it's like 10 times harder to prove a really strong version of the theorem that has really weak assumptions, that's often worth it, because then any consumer, anybody using that lemma later, if it's a frequently used lemma, has less work to do because they have fewer assumptions to provide, and they maybe don't need to prove their set S is open, and that's convenient for them, or they don't need to prove G is continuous. So we often do what Sebastian did, although this is a special example, and like work hard to make theorems as strong as possible. Okay, so I know that was quite a whirlwind, but the main thing I'm hoping you take away is we have like general powerful theorems of integration and differentiation, and we haven't really cut any corners, and we found they work well, and I encourage you to use them and think about them and so on. Okay, I'm done. Yeah, go ahead. Yes.
So yesterday in the algebra talk, we saw like this polygrid.
Oh yeah.
Kind of use like the Python script and use like
Yeah.
forces to
Yeah.
do some computations. Does there exist something like this for derivatives? Could there exist?
Yeah, there are, no is a short answer. It does not exist. Could it exist? Yeah, for sure. And it'd be really nice if it did. Yeah, there are people who are better, more expert at that side of things than me around, so I'm inclined to say less rather than more. But yeah, the short answer is that it does not exist, and it certainly could. I'm sorry. Yeah.
And you insert in your operators all series like this, and then put more stuff about matrices and exponential functions.
Yes, absolutely, you can. So the power series for the exponential that we were looking at, that was just ultimately it was set up in the complexes, I think, but ultimately it's just relying on the fact that the complexes are complete and have a norm, and are a complete normed algebra or something. And I think we possibly even do have exponentiation more generally. Again, I'm going to interrupt Eric, who might be distracted. Exponentiation of matrices.
Yeah, we have an entirely separate definition of exponentiation.
In Mathlib, like it's not. Yeah.
Yeah, for any normal algebra.
Yeah. So, yeah. Yeah. Because we just haven't. Okay.
And the reason they're not normal algebra is that we can't agree original and partial, so we've got no normal.
I see. Yeah, because we might want the L1 norm or the L2 norm or the L infinity norm. Okay, and so you have to say, I'm using this norm, and then the stuff works.
And this is actually a big problem about derivatives of matrices either, because we have to take which norm we're going to take it down.
Yeah, but we may solve this because we're considering generalized derivatives to any appropriate topological vector space. Yeah. Well, it doesn't have to be, but that's just the nicest way to solve it.
Either we solve it or we say 3 times everything we want to say about it.
Yeah, okay, yeah. Yeah, yeah. Okay, anything else? Okay. Thank you for listening. Now, what do I do with this?